Welcome to This Explainer. Today, we're diving straight into the sheer beauty of Go algorithms. And listen, we aren't just looking at code that happily breezes through the perfect expected inputs. No, we're going to examine functions that elegantly anticipate and completely neutralize nasty edge cases before they ever have the chance to become a problem. So if you love clean, resilient code, you are absolutely in the right place. Let's get into it.
Here's a quick look at our agenda. We'll start with the art of Go algorithms, then look at string parsing in fifth and skip, the concatenation trick in not decimal, backwards iteration in rev count alternate, and wrap up with some core algorithm design principles.
All right, section 1, fifth and skip, string parsing. So the goal of this first function, fifth and skip, is highly specific. It needs to keep exactly 5 non-space characters from a given string, and then entirely skip the 6th non-space character, repeating that pattern until the string ends. Now, at first glance, managing counts and skips and ignoring spaces all at the same time, that sounds like a total recipe for messy, nested logic. But as you'll see, the way this is handled is incredibly graceful. To pull this off without getting tied in knots, the code breaks the problem down into 3 very distinct phases. First, early guards to filter out bad inputs right out of the gate. Second, a tracked loop that enforces the 5-in-1 rule using dedicated state variables. And finally, a specific cleanup phase at the end. Let's break these down. Notice how those early guards protect the loop right at the top. An empty string just returns a new line immediately. But look really closely at that second guard, the one checking if the length of the string is less than 5. Because Go's len function counts raw bytes, this actually includes spaces. That means an input string, like 1 space 2 space 3 space 4, is actually 7 bytes long and bypasses the guard entirely. But a compact string like 1 2 3 4 is immediately rejected. It's a slightly blunt but super effective first line of defense. Once we're past that, the loop relies on just 2 simple state variables, count and skip. Let's step through that core loop using the alphabet. As we process the characters A through E, our count variable ticks up. The moment that count hits exactly 5, 3 things happen all at once. We append a space separator to our result, we reset the count back to 0, and we arm our Boolean skip flag by setting it to true. Because that flag is armed, the very next character, which in this first pass is F, hits a continue statement. It's silently dropped from the output and the skip flag is reset. It's like clockwork, and it repeats flawlessly for L, R, and Y. And this brilliantly illustrates why there's a specific block of cleanup code at the very end. Think about it. If your string perfectly ends on a group of 5, let's say the input was exactly ABCD, well, the loop logic dictates that a space separator gets appended right after that E. But since the string is over, that space is completely unnecessary. It just leaves us with an ugly trailing space. So the if statement at the bottom checks for exactly that and elegantly slices it off before returning. So why does this overall structure handle edge cases so incredibly well? It all comes down to cleanly separated responsibilities. Spaces in the input, they trigger an immediate continue at the top of the loop, meaning they never increment the counter or accidentally trip the skip logic. What if the string ends prematurely while the skip flag is armed? The loop just terminates, and the armed flag never fires. It's passive safety at its absolute best. Moving right along, section 2, not decimal, the concatenation trick. The objective of the not decimal function is to take a string representing a decimal number and convert it into a non-decimal string. Essentially, we just want to remove the decimal point entirely. Now, here's the crucial insight. Doing this mathematically is surprisingly complex. You'd have to parse the string into a float, figure out exactly how many decimal places there are, calculate 10 to the power of that number, multiply it, and then convert the whole thing back to a string, all without losing precision. Yikes. Instead, this algorithm bypasses the math entirely. It uses a brilliantly simple trick, literally slicing the string at the decimal point and just gluing the integer and decimal parts back together.
First up, a simple loop scans through the string character by character to find the index of the dot. If that index stays at -1, it means there was no decimal to begin with, so we just return the string as is. It also checks the slice of characters after the dot. If those decimals are just a single 0 or completely empty, the function is smart enough to realize that gluing them wouldn't change the integer's actual value, so it just chops off the decimal entirely and returns the integer portion.
Visually tracking this, you can see how straightforward it really is. The input 174.2 is split into 174 and 2, and then simply shoved it together to become 1742. Now, the source material does point out an interesting nuance here. If the input is 0.1255, raw concatenation gives us 01255. The expected output in the system is actually 1255, meaning leading zeros are dropped. The source deduces that either the caller handles this cleanup or the evaluation system parses it dynamically. Regardless, the core logic of dropping the dot via concatenation, it works flawlessly. And what's super interesting about this function is its extreme resilience. Because it treats numbers as dumb text, negative numbers naturally keep their minus sign. It's literally just part of the first string slice. Even completely invalid garbage strings like -0.0f00d00 won't crash the program. The function finds the dot, splits the garbage text, and safely glues it back together without a single parsing panic. It relies on the system to provide valid floats, but it absolutely refuses to break if it doesn't.
All right, section 3. Rev concat alternate, backwards iteration. The premise for this one is a bit of a brain teaser. This function takes two slices of integers and concatenates them in reverse order. It alternates picking elements from each slice, but with one strict rule. It must always give priority to the larger slice. Let's see how it pulls that off. The core mechanism here literally flips the traditional for loop right on its head. Instead of starting at index 0 and moving up, the code first figures out the absolute maximum length between the two provided slices. Then, it sets up a loop that deliberately iterates backwards, starting out that maximum length -1 and counting all the way down to 0.
But why go backwards? Well, by starting at the highest possible index, we guarantee that any extra elements, the ones belonging exclusively to the longer slice, are processed first. Since we're dynamically building a new result array by appending elements as we go, processing those high index elements first ensures they end up right at the very front of our final returned slice. Let's trace this with two equal length slices. Slice 1 is 1, 2, 3, and slice 2 is 4, 5, 6. The max length is 3, so our loop starts at index 2. The primary condition checks if the length of S1 is greater than or equal to S2. Since they're equal, it's true. So we append from slice 1 before slice 2. At index 2, we append 3, then 6. At index 1, we append 2, then 5. Because that top-level condition is locked in, slice 1 reliably leads the alternation the whole way down. However, when dealing with unequal slices, the source document notes a really interesting discrepancy. Because the code evaluates priority based on the total original lengths of the slices, it locks that priority in permanently. If slice 2 is longer, slice 2 leads the entire time. But the source points out that the expected output actually suggests the priority should flip mid-loop once the remaining uniterated elements equal out. The code, as written, is rigid, which perfectly highlights just how tricky dynamic priority state can be in loop design. But despite that highly specific edge case nuance, the safety of this loop is completely locked down. Every single append operation is wrapped in a strict I<len boundary guard. That ensures absolute index safety. If one slice is empty, its guard never triggers, and it's ignored. If both slices are empty, the maximum length is 0, the loop fails immediately, and it safely returns an empty slice. Literally zero chance of an out-of-bounds panic. Finally, section 4, core algorithm design principles. Now that we've mapped the distinct behaviors of these three functions, let's zoom out a bit. Across strings, floats, and integer slices, we consistently see three hallmarks of highly resilient Go code. Number 1, defend your core logic loops by dispatching invalid edge cases as early as possible with guard clauses. Number 2, work smarter, not harder. Leverage native language properties, like how string concatenation effortlessly bypassed float math. And number 3, enforce strict index safety, so your program degrades gracefully rather than crashing hard. As you go off to design your own algorithms and tackle difficult constraints, I want to leave you with this final thought to ponder. How resilient are your loops to edge cases before the core logic even begins? Thank you so much for joining me on this explainer. I really hope this gives you a fresh perspective on writing bulletproof code. Keep building and keep exploring.